Hello and welcome to a special edition of the DCF Show Podcast. I'm Matt Vincent, Editor-in-Chief with Data Center Frontier. At the 2025 DCF Trends Summit last August, one of the defining conversations focused on a central AI era question, if not the central AI era question: how to power data center growth when the grid can't keep pace. Since then, grid constraints and interconnection delays have only intensified, pushing on-site and behind-the-meter strategies to the forefront of infrastructure planning. Given how urgent this shift has become, today we're replatforming and updating that power discussion for 2026, bringing back much of the original panel and adding fresh perspective. That summit conversation was led by Fengrong Li, Senior Managing Director at FTI Consulting, and we're pleased to have her back moderating today. Fengrong, over to you.
Thank you very much, Matthew, and welcome to all the fabulous panelists today for a highly informative session. We're focusing one of the most urgent topics shaping digital infrastructure deployment, that is on-site power and the rise of co-located integrated power and data center AI campuses. And these models has accelerated data center to expand beyond traditional hubs and reshape the redundancy strategies and changing how data centers are interacting with the grid. We're honored to have industry leaders today across the data center and power space, each bring a unique solution to provide reliable and scalable power solutions to power these critical infrastructures. Please join me in welcoming our panelists, and we would love to have each start with a brief intro of your role and your location. So I am in Washington, D.C., and happy to be your moderator today. I'll pass to you, Vol, please.
Hi, my name is Ival Bahar. I'm the CEO of ECL, and our headquarters is in the Bay Area, San Francisco Bay Area. We build data centers all over the place, but that's where our headquarters is.
Brian, please.
Sure. My name is Brian Gitt. I lead business development at Oklo. We're an advanced nuclear energy company, and we design, build, and operate power plants to power AI factories and cloud data centers.
Amazing. Marty, please.
Hi, everyone. Marty Trevette. I'm Senior Vice President of Energy Solutions at Alpha Structure. And Alpha Structure builds on-site power plants for these data centers for behind the meter, typically. Where our headquarters is in Boston, where we have a network operating center that manages these sites. And we use a financing model. So we design the system, finance, build, own, operate, and maintain these energy systems.
And welcome, David Blank, please.
Yeah, thank you. My name is David Blank. I'm the head of gas turbine sales in North America, and I'm based out of our Orlando, Florida offices. Thank you for having me.
Thank you, David. We can get started. So let's start at the highest level. On-site generation is becoming very increasingly competitive, but it is a fragmented space where there is no standardized solutions. That means we got to be able to integrate and innovate a lot in this space. So how would you categorize the current state of on-site power for large-scale AI data centers, and what trends are shaping the adoption today? This is an open question to the full panel, please.
Who's jumping in first, David?
Sure, I can jump in first. So thanks. I would say it's in its infancy. I mean, I'm of course coming from the OEM perspective. So we're of course selling our turbines for behind the meter applications, and this is a relatively new application that we've entered into, I'd say, within the past year and a half. And like you said in your question, we see that our customers are trying to figure out how to make it work. They're buying the turbines, and now they're kind of going towards, okay, now what's next? And to your point, there's no real standardization. We see that one customer solution for what they think will work will not work for the other. So I think it's this whole behind the meter concept is kind of in its infancy from my point of view, and everybody's trying to figure out how to make it work out, especially at large scale when you're talking about behind the meter. And what's driving this, I mean, again, from the OEM perspective, every data center wants to connect to the grid, right? If they can't connect to the grid, they go to a place where they can connect to the grid. And only if that isn't the case, then they consider it behind the meter. So, I mean, the driving factor behind this, from my perspective, is clearly the inability of data centers to gain reliable access to the grid for 5, 10 plus years at a time, especially at the capacity requirements that AI data centers are requiring, which are multiple gigawatts of power in some cases.
In a lot of ways, it seems like we're going back to the future because in 100 years ago, and as we've evolved through industrial history, all large loads had their own power plants, whether you're cement plants, steel plants. They had on-site generation because they needed on-site generation. And so I think in a lot of ways, we're just going back to our history or to our roots. Obviously, this is new for data centers, but not really. I mean, data centers have obviously their on-site power generation, but it's just more backup power and diesel gen. But I don't think what we're doing is some new and novel kind of technology breakthrough. It's just application of this technology in a different use case. And I think the scale of this is just immense. I mean, I think even this week where we're seeing kind of announcements like SoftBank coming out with a 9.2 gigawatt power plant. Who knows what that's powering yet? They haven't shared all the details in terms of if it's for co-located load or not, but basically it's likely being built for servicing a lot of this digital infrastructure regardless. So I think what we're seeing is the scale is we're talking about, that's all, just using that example, that is the largest power plant in the history of the United States, right? And that is the scale that we're moving to. These campuses are 5, 10 gigawatt campuses is kind of the direction of travel, not obviously turning on today, but that's kind of over time, the master plan. And so when you're talking about that much power in a location, you're going to have captive power plants. I don't think there's going to be any other option. The grid, there's no way that the grid is going to be able to handle that amount of growth in the timeframes that we're talking about. And so I think these configurations and these deployments are going to have to figure out how they integrate into the grid and contribute value, and as a good grid citizen, give back to the grid. I don't think the reality of having behind the meter forever is going to work or going to be politically palatable. And so I think getting these going for speed to power is going to be essential, but then having a plan and a phased transition of how these assets can continue to power the data center capacity or the AI factory, but they will also contribute to the grid and be grid connected eventually once the grid is able to.
I personally think that those data centers that will actually go behind the meter will never go back to the grid. I think in the situation we are in right now, where the grid providers indicates to us it's going to take them 5 to 7 years to catch up, and they're already catching up for something that we can't predict what will be the catch up to. We will have to actually be self-sustained, building data centers that can actually be self-sustained. Even if politically people will try and enforce the data centers to first fund the build out of the grid, and second be more or less devoted into allocating the power back into the grid, it's going to be a challenge financially because data center operators have a certain commitment to their customers of how they can actually maintain availability. If the grid has the power to actually pull the power from the data centers, what happens to those SLAs? So there's a major challenge on a business engagement model, how to actually do a temporary pre-grid and then post-grid where we're actually expected to push back into the grid. I think on one more thing that happens right now is we have an opportunity to innovate on how power is being generated. And that's an area that was used to be just assigned to the utilities and the engineering groups of the utilities, and suddenly there's an opportunity for people to come and say, "Yeah, I can do it just as good. I can do it in some cases even better than what you do at a lower cost and definitely at a faster turnaround. I will do it." It's a lot of people are saying we're not going to wait for the grid, and when the grid comes online, it's going to be too late anyways. The grid are planning to have a solution in the next 7 to 10 years when they don't know what the problem they're trying to solve in the next 7 to 10 years. We have a problem right now. We're short on power.
Yeah, all of these points I totally agree with. I would add one additional one that we haven't mentioned here is the financing piece. So one of the reasons for on-site power is to contain the expense and the rate, so it's not passed on to the rate base. Basically, if you have on-site power, then the data center off-taker, the hyperscaler or the hypercolo, can contract that for that power on that site, and there's no mixing of financial paths. So there's no a lot of the pushback right now is, okay, you're going to build all these data centers on the grid, and as a ratepayer, us, at our homes, we're saying, well, our rates are going to go up. And that's not necessarily the case. It's very clear if you do on-site power finance just for that on-site power site and just off taken with the data center operator, then there is no cross-pollination of rate base. There's no discussion, but if you go that model. So I'm seeing that quite a bit now in the discussions, is to keep it clean, keep it behind the meter, and keep it financed that way. I don't know if that's going to be the end all be all future. As Brian said, in the past we've done this many times. I've been to countless sites that have, say, a 50 megawatt gas turbine that they built their own site power, or coal plants even, and they're mothballed now. They're no longer in operation. But the reason they did that at the time, say 50 years ago, they couldn't get enough power from the utility. But once the utility did come along with enough power, it was cheaper for them to switch over to the utility and operate it that way. So I think there's going to be kind of a mixture in my mind of both. But I agree totally that the rate of change here, and once you have a really good operating system behind the meter, if it's cost effective, why move to the grid? So I think there's going to be a mixture in my mind. So.
Excellent insight. So we have seen, being in consulting, we see a lot of projects in this space, and I agree with you all. The speed and the control, the complete control of the build out schedule, really dictates, drives the growth of these business models. And Marty, to your point, once the financing, the contracts are lined up, you're locked into this take or pay position to perform under the contract terms. And then there is, could be flexibility at the end of that contract to reconfigure, but during the contract terms, it's basically performing under the performance and the contractual guarantees. And I think that's what drives Yuval, your comments. A lot are going to stay behind the meter because they have a contract to perform.
Yeah. And I think the one thing which is very interesting is when we generate behind the meters, first you own the facility. So you own your own generation, you control your own destiny. And the second thing is, at least in the US, you're allowed to actually sell the power at whatever price you want. So for data center operators, there's a motivation to actually do self-generation, because if you know how to do it very well and you can produce it for a lower cost, you can actually have an additional revenue source, an additional profit source just by selling the power instead of having a third party which is actually making their profit. So there's a lot of motivation in first time to power, right? That's the key, or time to token is the key, right? And that's the first motivator. But there's other business motivations to do that. And since there's so much demand on the grid, I don't think anybody is going to be forced back into the grid at some point, because the demand will still continue. And a bigger problem that we have right now, we're talking about the large sites, but the bigger problem that we have right now is in the small sites, is in the inference sites. The inference sites are coming closer to the cities when the power is even more scarce. And that's creating even a bigger problem, because in the cities, we're getting 3 to 7 years response time from the utilities, at least in California over here, you can get power until 2030, 2031, and we need to build inference sites now. So we have to go behind the meter for these solutions when you go to the inference sites. And that also makes it even more interesting to actually be able to do modular power instead of centralized power, which is a very interesting concept that I'll be happy to discuss further.
Excellent. This panel each bring a very unique solution and actually touch from the very modular solution to all the way to gigawatt energy intense, potentially in remote sites. So I think we'll have a good conversation along that very big spectrum. Now want to touch on a second common question. When weighing on-site generation, with different technology configurations, that really shifts the definition of redundancy strategies, the water requirements, permitting strategies, as well as the backup power, all the way to fuel selection. So want to open that very broad question to this panel, tying to your experience. Can you provide the audience a flavor of how that on-site power is impacting all these secondary and tertiary design elements to bring a data center online before the grid could supply power?
Yeah, I can start again. In short, it changes everything, the shift from being on grid to going behind the meter and trying to manage that behind the meter. Obviously, you have all the complications now of building a utility scale power plant, especially with the size of gas turbines that I represent. You have to build a utility scale power plant in itself, in a market that's already very saturated with activity. So can you find an EPC that can construct your power plant on time? Can you get a gas turbine? Can you get your transmission equipment? Can you get your permits? How's your gas? How's your water? So you have to get all of this done. And you have to figure out how you're going to manage this power plant to function behind the meter, behind the data center. So, if you've got a data center where loads are going up and down hundreds of megawatts in milliseconds, how are you going to handle that? What type of transmission equipment do you need? Then you've got, okay, well, what's your data center reliability that you need? So you got 3 nines, 4 nines, 5 nines. How are you preparing for that? Do you need backup equipment for the primary equipment? Do you need backup fuel for your primary fuel? So it opens this plethora of questions. And relating back to your first question, there's no real way or no standard way currently to address it. So there's a lot of ideas and a lot of solutions and things that are already being built, but it's definitely a big challenge to go from on-grid to full behind the meter, especially for large-scale applications.
Yeah, one thing I want to add to that is when you look at behind the meter, there's one way to solve this, is what David was describing, is build a power plant. But there are other ways to do it. And one of the ways that we decided to take is completely distributed power plant. So we don't have a centralized power plant. Every block of 1 to 2 to 3 megawatts has its own power generation system with the redundancy and with the availability that it requires. And you put a lot of them together to build large sites. So we build a gigawatt site built out of 2.5 meg blocks. So that's a lot of blocks in there, 400 of them, but we don't have a centralized power station to manage. We don't have transmission. We don't have to deal with all these things. We don't have high voltage. Everything is actually generated 480 or generated DC level. And then the transmission is like 10 feet because the generator is 10 feet away from the block of the data center. Simplifies a lot of problems that we can do if we do grid. And you also get an opportunity to get much more sustainable if sustainability is important for you. Sustainability today on the grid is non-existent, more or less. There's a lot of talk about this, but the grids in the United States are going to be relatively contaminating the air for a while, probably next 10 to 20 to 30 years. And if you do your own generation, you have an opportunity suddenly to actually make a sustainable generation and make a dent on the ability to generate energy in a sustainable. And I think Brian probably can vouch for that on the solution that they have on creating a sustainable energy generation.
Yeah, I think each project is going to have its own unique configuration based upon the requirements and what's available. I mean, right now, even you're seeing basically because there's supply chain constraints on gas generators that they're cobbling together. Projects are cobbling together some recips, some turbines in different sizes and ramps into larger sizes as they go. And I think there isn't going to be a one size fits all for every project. Every project is going to have its own unique needs, and depending on the time frame and what they're optimizing for, they might make different decisions about the equipment that they purchase. So all this means that there's going to be generally more cost involved, I think, in the near term, because what they're optimizing for is speed over cost. I mean, the grid in general is going to be a cheaper solution traditionally, now not in all cases, but then because basically you're recreating the grid on a very small scale on your site, and there's a lot of costs that you have to factor into that. So it's going to inherently be more expensive generally, but that's okay, especially for a lot of these AI use cases where represents massive opportunity and revenue potential and value. So I think it's going to be somewhat bespoke on a case-by-case basis, the integration of all these energy technologies and whether you have battery energy storage and what types of generators you have. And I don't think there's going to be just one configuration. And then over time, I think we'll try to standardize as much as we can, but I just don't see that in the near term to have kind of one standardized cookie cutter model.
Yeah, I agree with that. We have several different designs that we use, and from some of them they're 100% fuel cells, and then some of them are a mixture of DERs, and then the bigger ones are gas turbines. So just depends on the size, and if it's a local inference in a city, then it's smaller size. So then you got the emissions to deal with, so it's probably going to be something toward a fuel cell arrangement for those situations. Then you got noise, sound abatement you need to do in certain areas. So yeah, they're all like snowflakes a bit, with some standard modularity to them from what we've seen in the projects we're working on.
And that partially is the appeal of this space, just how fascinating it is, because each case is solved specifically to the site situation and to deliver I guess, an overall balanced cost benefit solution. Now, thanks for all that very nice insight. Maybe we can break into I'll ask some one-on-one questions because each of you, the technology is different. I think the audience will appreciate a little bit deeper dive into the technology. And if okay, I will start with you, Vol. ECL is known for pioneering really modular, distributed, hydrogen-powered fuel cell. And you mentioned each one is on a one-on-one power to a modular data center. That design alone is quite unique. So for a data center owner and operator, what are the biggest appeals of this type of system versus for lack of a better word, a centralized, bigger size power plant?
Yeah, thank you for the question. It's a very interesting question. The main advantage that you get, especially when you localize your power, is that you do not have to deal with concentration of energy in a single point of generation. Now, when you do concentration of energy, it gives you advantages because you can actually create a better redundancy level, etc. But the challenge with it is, I think, like David mentioned before, is, for example, with AI workloads dealing with transient. The grid is capable of sinking and pushing power at very high speeds, at very high currents. Local generation with turbines or with recips cannot do that. So you have to build something else around it to wrap it. And when you do it localized, you can actually isolate the blocks that require this from the blocks that don't require this. And when we do it with hydrogen, we also zero emission and zero water, because when you generate energy with hydrogen, there's zero emission and the byproduct is water, which eliminates another challenge that we have in this world, which is people resist data centers when they come to the communities. If it's for air pollution, if it's for noise, if for anything else, when you come to them and say, I don't have any pollution and I'm not going to touch your water, it's going to be a completely different response. Now, for that to scale at very large scale, you can do it in a centralized or in a distributed way. But distributed way we found to be, first, more cost effective, surprisingly enough, and second, give us the ability to scale at the pace of the technology. And that's something that is we're living day by day in and day out. The technology pace right now for AI is about a 9 to 12 month cycle. None of our technologies for power generation can actually catch up to that scale. We don't change technology. We don't change turbines every 12 months. A cycle to develop a new turbine is 36 months usually. So how do we actually catch up with the density that is required by the future generation? We started at 50 kilowatts per rack, moved to 125, moved to 150. Now we're building 300K per rack on the same space. We need to feed that. And what we do is we scale our generation plants outside per block. That means that the blocks that will be required at the end of 26 and early 27 will not look the same as the ones in 2025 or 2026. And that when you do it localized, you give you that huge advantage of doing it per block for the future. So you don't have to actually pre-plan years ahead of time, decentralize how I'm going to deal with a certain amount of power. The second aspect of that is an interesting thing. Its supply chain is becoming simpler. And why does it become simpler? Because you don't deal with the same components that everybody's fighting for, which are the large transformers, large switching gear, high voltage equipment. You don't need to do that. You can actually generate at low voltage. And in our case, we generate DC. We bring DC into the data center. We don't even have AC delivery to the data center. That makes it even more interesting and more simple to actually manage your supply chain to build at scale.
Amazing. Related to hydrogen, that's fascinating. I know your project in Texas are being constructed. What are the thoughts as you move closer to the city where hydrogen infrastructure are not there? How do you see the industry solve that problem, fuel supply problem?
Yeah, so there's two ways to address it. For small sites like the one we have over here in Mountain View, we get delivered liquid hydrogen. It makes the cost of the energy more expensive. But in certain areas, the price of the grid is so high that even if you get liquid hydrogen delivered to you, you're still competitive with the price of the grid connection. The other option is what we announced a week ago, which we call flex grid. We can actually pull either hydrogen or natural gas with carbon capture or grid and mix them together. We have a unique novel technology of mixing different sources of energy together and delivering to the data center AC or DC power. And that gives you the ability to do it. We do it with fuel cells on the DC side. We do it with the batteries, best batteries, etc. Architecture, one thing that we're talking about the innovation of how to do this with hydrogen properly. Architecture completely modified the traditional data center architecture. We don't have a UPS system and we don't have a diesel generator as backup. We have an active environment where all the sources of energy are pushing energy at the same time. And they're balancing each other, they're shaping the power for each other. They do a lot of things like that. That's things that you have to do when you do it modular and do it small. And with hydrogen, you can do it up to a scale of 7 to 10 megawatts of hydrogen-based delivery is still reasonable. Beyond that, on delivery, it starts to be a challenge because you're going to get too many deliveries into the site. It starts to disrupt the site. So if you go to small sites, for example, that have 5 meg on the grid and you add to them another 10 or 15, which is a mix of natural gas and hydrogen, you can actually create a significant 20 meg site with a combination of all the options that you have. Because even if you go to sites that do have natural gas to them, Usually in the urban areas, the pressure and the flow is going to be too low to be able to build very large scale. So you have to mix all the options that you have. And I think that's the approach that we're going to have in the next few years. We use every source of energy that we can get. If it's renewable, combined with natural gas, combined with hydrogen, combined with whatever other technology which is out there to satisfy the demand. The demand is so high right now.
Thank you.
One comment on that. In Texas, when we have access to a pipeline, we're building multi-gigawatt site. So when you have access to the pipeline, then you actually can be very, very competitive. And the price that we generate energy with is actually highly competitive to the grid price. So it's not that you pay a penalty from being actually off grid on hydrogen.
Amazing. Yes, I like how your technology are thinking ahead and adjust to the geography and the location and deploy customized solutions depending on the fuel infrastructure and the capability of the site and the fuel supply. That's fascinating. And now to Brian. So first, congratulations on massive progress on Oklo's technology advancement and also your recent deal with Meta to deploy 1.2 gigawatt in Ohio. So can you provide an update on the powerhouse and what's coming down, what has been the progress in the past few months? And we know that the model really is significant because it allows hyperscalers to provide funding to enable these very capital intensive new generation capacity to attract private capital and to get deployed. How do you see this model being replicated and expanded to and have an impact on hyperscale power procurement and also, more importantly, accelerating these critical infrastructure development?
Yeah, thanks for the opportunity to share a little bit more background on that. It's a very exciting way to start the year to announce this 1.2 gigawatt deal with Meta in Southern Ohio. We've been working on it for a long time, so finally making it public is it's great to start getting that word out and educating folks on how the deal works. But I do think it's actually a good model to talk more broadly to answer your question directly. Take a grid like PJM on Mid-Atlantic, 70 million people. It's the largest grid in the US. And what Meta's strategy is, I think, is kind of an evolving strategy for the industry, which is we'll see as the final rules shake out with FERC and what's happening at PJM. But basically, the writing's on the wall. If you're going to connect 1 megawatt of load, you're going to have to point to and bring 1 megawatt of gen. It's going to be one for one, whether you do that on-site or off-site, but you're going to have to be facilitating through your agreements, bringing that additional generation on. And that's, in essence, what we did with the deal with Meta. So we're not co-located with Meta. We're basically injecting energy into the grid in Southern Ohio and providing capacity to that market. But it's going to be helping to power data centers in Ohio and in AEP service territory. And I think those are kind of the filters that a lot of the hyperscalers are starting to use, is that it doesn't have to be co-located, but they need to be able to point to the generation, the additionality that they're bringing into the region that they're putting large scale load into. And these projects are going to be phased both on the load and gen side. And that's one of the strategic advantages of Oklo's size. We build 75 megawatt power plants and we scale them in Lego-like fashion as you build out a site, a master plan site. And we can be co-located or not, as in the example with Meta. But this enables you to synchronize and coordinate the build out and build much faster. I mean, we can construct these things in 18 months. Now, the full lead time when you factor in licensing and regulatory and long lead procurement and all of that, we're aiming for about 36 months from a signed binding power purchase agreement to commercial operation date. Obviously, our first projects are taking longer than that, getting through the gate and getting all this stood up. But we have line of sight of achieving that in the near term. And once you're starting to build the initial phases, because we're building in these blocks of 75 megawatts, you can build multiple blocks in parallel. And so you can start bringing 300 megawatts a year onto a site and then scaling that over time as the load increases on that site. And so I think it's a model that I think is perfectly right-sized for the data center industry. I mean, although the requirements per rack, as was alluded to earlier, is getting crazy. I mean, the amount of energy density and just the power requirements. But in general, I think building in 7,500 megawatt blocks is kind of a nice size. Once you start flipping over to building much larger power plants, now you've flipped over into what I would consider mega infrastructure projects. And that in the nuclear industry has been the Achilles heel of the industry. The recent experience in Georgia with the plant being 7 years behind schedule, $17 billion over budget. There's a lot of reasons for that. It's complicated, but one of the big reasons for it is how big and complex this mega infrastructure site is and how many various people are involved and entities involved. So by building smaller units and simplifying that and pulling a lot of that low productivity construction labor into a high productivity manufacturing environment enables you to scale in a different way than just building bigger power plants. So I think what we're seeing is more smaller modular approach, whether it's my colleagues here doing gas gen or fuel cells or advanced nuclear. I think that is the direction of travel. And that's how data centers and AI factories are built already. Even these largest campuses, no one is turning on 500 megawatts or a gigawatt all in one day. I mean, it's happening in successive builds of buildings on a site. And so you want to coordinate and right size the build out of your power infrastructure with your digital infrastructure. Whether it's co-located or injecting in front of the meter, I think both still apply. So that's the approach we took with the Meta deal and that we're seeing kind of across the board.
That's a enormous progress. I can imagine a framework agreement like that provides certainty as you move along all the key milestones and drive these sites into commercial operation in a phased approach, which is really it's interesting the size you commented on, and that's what we have seen in the gas space as well. So maybe that's a great segue to David on the gas side. As the AI-driven data center demand drives both not only demand, but also the density of the demand and the firmness of the capacity, we saw really record level of demand for advanced frame and aeroderivative turbines to record levels. Even when the OEMs scale the capacity, the market still remained underserved. Want to ask you fundamentally, how do you see turbines serving as the near-term backbone for hyperscale growth, but also in the longer term, a bridge to low carbon firm power solutions? And then I have a secondary question. Everyone wants to know about the timeline. If you could comment on the timeline with large frame and the smaller frames.
Yeah, for sure. So as you mentioned, our gas turbine sales have been very strong over the past year or two. And frankly, our gas turbines, given the inability of data centers to access to the grid, to get access to the grid, our gas turbines have been the enabler for data center growth. I mean, our gas turbine technology or gas turbine technology in general is not new. It's proven, reliable. It's very power dense. You can get a large amount of capacity within a relatively small amount of space. So yeah, gas turbines are clearly a big piece in allowing this data center boom move forward by allowing it to achieve and get the power that it needs. So I see this happening, well into the near term and the midterm. You mentioned other fuels or lower carbon in the future. Our turbines have the ability to run on alternative fuels, including hydrogen or other types of fuels. So depending on customers' access or the ability for them to access those fuels, our gas turbines, which are relatively clean in the first place, can even get cleaner by running alternative fuels through them. In terms of lead times, we've experienced a once in a generation boom in our industry, in the gas turbine industry. And it's resulted in longer lead times that have been typical for the past 20 years, if not longer. So right now, I mean, to get one of our largest gas turbines, you're talking easily into the 2030s. As a general rule of thumb, the smaller the turbine you go, the faster lead times you get. So for our smaller gas turbines, we're in the 2020s for lead times, but for our advanced class turbines, we're right at 2030 right now.
Yeah, thank you for commenting on the few multi-fuel strategies. We talked recently extensively to IPPs, utilities, and to data center buyers. And top on the buying criteria, the dual fuel or multiple fuel capability is not just a checklist, it's a real binding criteria that's very important. I think in the longer term, the buyers wanted to be able to switch to a higher percentage of hydrogen or a cleaner fuel when that is available.
Mm-hmm.
That's great. And moving to alpha structure. So Marty, your projects, you deliver multi-technology and design, build, own, operate, finance. You do the whole campus, and your solution not just to data center. You serve airports, you serve key critical infrastructures. So very curious, what type of generation and storage technologies are you deploying more frequently today for both primary and backup power? And how have you seen that evolved with the rise of the AI workload where there's sharp swing? How do you integrate different components of technologies to specifically ensure the islanded microgrid can handle all the voltage, all the swing, the load following, and of course the reliability of the generation?
Sure. That's a big question. We can spend a week seminar on this and walk through it. But in general, we're looking at, and it depends, like I said earlier, it's kind of a snowflake depending on the use case for a particular site. And certainly we want to use all technologies where they're the best suited, the ECL and Oklo reactors. I mean, we definitely want to use those in our mix. It might be for future projects, depending on availability or depending on the lead time or whatever. But today it's mostly around a mixture of engines, fuel cells, and gas turbines. Some of those might be combined cycle gas turbine plants, some, with steam and everything else, but it just depends on how big the data center is, what the timeline for the data center is, and so forth and so on. But most of them right now, this minute in time, are a combination of either engines, fuel cells, or gas turbines. And some of the projects have all of them on for various reasons on the same site, depending on how they're going to phase, how big the data hall is, everything else. You mentioned, I'll take the next one, is kind of load following. So load following, as David mentioned, could be from the big campuses, could be 100 megawatts in seconds or even some sort of high level milliseconds. So you got to be able to follow that. So we typically use a combination of, if we do have to have extreme load following, then it depends on how extreme of load following with the load curve, right? Then we would put in maybe a combination of a supercapacitor, flywheel, along with the battery storage, along with load banks. So all of those, so you can track up and track down the energy. So there's a combination of all those assets to do fast load following. Now there is a movement afoot with changing the load following parameters at the server. because every time I think you've all mentioned it, it's time to token. So every time you have these spiky loads, you're losing compute time, and it's usually around. I mean, there's no certain number here, but it's like 100 kilowatt hour for every billion tokens on average, right? So every time you have one of these spikes, you're losing compute time and you're losing tokenization. So what a lot of the NVIDIA, AMD, all these companies are working on solutions at the server to smooth out that load with filler loads, filler jobs at the server themselves, so that that's a win-win-win. It's a win for tokenization, but it's also a win for on-site power and even the utilities trying to load follow these extreme spikes. Additionally, it depends on what uptime institute. If you use the Uptime Institute kind of characterization for data centers, there's a tier one, Roman numeral one, 1, 2, 3, and 4, right? If it's a tier 3 or 4 data center, it's going to have a double conversion UPS system or open compute UPS at the rack or at the compute center that's going to be inherently able to load follow most of that load. So that smooths out the needs that you're going to have on the power plant side. A lot of these AI data centers, though, are tier 2 data centers, and the tier 2 data centers will not have necessarily UPS on the loads. Then that's what I call extreme load following. So if we find out it's going to be a tier 2 data hall, then we know we have to institute extreme load following. And then that would pull in supercapacitors and flywheels and all the other subject matters that we have. And Siemens, I saw David shake his head. They have a product called Blue Vault, which is a nice battery storage combined with the high speed like supercapacitor on the front end. And there's a lot of other solutions out there. So it just depends on how we combine that. And then for backup, so we're seeing a movement in the backup side going from tier 2 emissions compliant like diesel or natural gas, quick start, fast speed engines. We're seeing a movement away from, kind of eliminating those and using more battery storage, using more generation assets. The ECL modules, they're high availability because you can get so many of them on a footprint. So you can design a system that you have inherent backup already, and you just don't need those, or you diminish the volume or the number of those purchases of those quick start backup engines that are just sitting there with low utilization rate. So it's a combination of all of these factors that we put into this mixture with the clients and walk through kind of a solution for them. And at the end of the day, we have to try to make it as reliable or more reliable and available than the grid, right? Because that's the bar that's set for us to make sure, 99.9 availability, 24/7, 365, right? So we could spend a lot of time on this, but that's a high level of how we approach.
Really insightful. In the end, you're dealing with this level of complexity and the integration, making sure all the pieces perform together and to achieve the level of load following and reliability that's needed for the end use customer. So going back to, if you're talking to an end use customer who used to buy from grid, and that's simple and easy to understand, but now they're buying a solution for behind the meter, what are the biggest convincing or the biggest hurdle, or maybe it's appeal in these days, because a lot of players would want one of your solutions on the campus. Can you comment on that? Just how the industry have come to embrace these microgrid, and many are islanded microgrid solutions.
Yeah, it's certainly been a journey. I'd say some of the early adopters of microgrids or on-site power was really in the electric vehicle transit depots with municipalities and big depot agencies where they need a level of resilience. They're in a very urban area. So getting power from the grid is going to be, even if they could get the power, which in those cases, you could get the power from the utility in a shorter enough lead time, but it's super expensive because you got to tear up city streets and put in new substations, and it just gets really expensive. Plus, you need an on-site backup for those EV chargers, like a storage, if you think, like a battery storage, and and solar to be able to charge those buses in the lack of utility fee. So that's a little bit different use case. Airport's a little bit different use case. And then you fast forward to data centers in that use case. There's a lot of reluctance 2 years ago for on-site power, when 3 years ago, hey, we can get everything from the utility we need. And now the power demands get more and more and more, and you just can't get all of that in the time frame you need, time to power. So it's almost like now it's shifted in conversations to, well, we're going to have to do some level of on-site power. So how do we go about doing that in the right way? And then, how do we finance it? And what does that look like? Because it's been really kind of straightforward financing with the utility up till now, and there weren't even really take or pay kind of relationship or contracts until recently as well. So now everything's like, all right, heightened sense of awareness of the cost of power, the availability of power, the reliability of power, the backup. So we've seen a shift in mindset now of it's necessary and we're going to have to build on-site power. So let's do it the best way. And how do we do these long-term contracts, and how do we do the backstop financing and these power purchase agreements and the contracts accordingly? And we've also seen the time duration of a power purchase agreement increase. So when we first were working in the data center space, they were like, give me a 5-year or a 3-year power purchase agreement. And then you're in kind of a rental state where you're just renting units to get them up and running. Now they're looking at, hey, we don't want to waste time with all that. Let's go to a 15-year contract because that lines up a little bit with what we're doing with our hyperscalers and so forth and so on. So we've seen a real shift toward more pro on-site power and it's been dramatic in the last 8 or 9 months.
Thank you. And that's a great segue. Before we wrap, I know we have about 3 minutes. I want to broaden the topic to everyone. On-site power, as we discussed, requires substantial capital, very customized design and solution and elements of technologies to be integrated. So it needs certainty. And that comes from hyperscale step in early to provide that certainty. And that comes from contract structures, longer duration take or pay. So how are contract structures such as take or pay, contract duration, and credit requirements affect the pace of on-site power development? And how have you seen, how early do you see the end-use customer step in to provide different levels of certainty to make sure the project move along, key milestones eventually get built? So that's to the whole panel, please.
I guess I can start again. So at Siemens Energy, we generally don't contract with the end user, the data center itself. Usually there's an intermediary, so I can't speak specifically to the contractual terms of the PPA itself. But what I can comment to is that when we look to transact with an entity for a data center application, we are very selective, and we absolutely make sure that there is some sort of commitment from the off-taker, whether it's a co-locator, hyperscaler, what be it, that somebody will off-take the power before we even entertain a conversation for a transaction for our turbines.
The way we're handling this is doing power prepayments or capacity reservation deposits. And so we're getting a capital contribution from the customer to reserve specific amount of capacity. And then we're taking that money and signing take or pay fuel contracts. That's really ultimately our longest lead big bottleneck is fuel. And so that's one of the ways that we are giving project certainty is that basically that customer is locking in X amount of capacity for their project. And we're getting that capital contribution up front, whether it's in a power prepayment or a capacity reservation deposit.
Yeah, in our case, what we do is we sign long-term agreement with the providers of the fuel. And we try to be on grid from their perspective, means on the pipelines, which are already serving multiple types of other technologies. Like, for example, hydrogen is serving petrochemical and other industries which are using it. So they have very high level of capacity. The one thing which is challenging is growth. If we need to grow dramatically, we need to at some point have a participation in the cost to actually grow the availability of the fuel. But the one thing which is helping the people who build data centers right now, if you look at the costs to build a data center, including the power generation plant, compared to the cost, which is the equipment which has been put inside, it's a ratio of a 1 to 4 to 1 to 6 or 1 to 7 in some cases. So the customer is much more easily willing to operate with you and enable you to be able to fund some of this investment that needs to be done because it's becoming an insignificant part of the overall cost to build the infrastructure that they need. So we found our customers willing to participate in the cost to actually build the self-generation plant and then make sure that the self-generation plant are maintained properly because maintenance is also a significant portion of it once you build it out.
Yeah, and I can summarize all these points where we're seeing as well. It's all of that. It's the deposits on the equipment or fuel, lead times, and then having to to get it financed, you got to have a credit worthy offtake and backstop generally to make that happen. So, and the credit worthiness dictates the price as well. Just like any economic model. And it's kind of like buying a house with a mortgage and getting your interest rate and everything else. It just kind of all fits together as one big puzzle that you're trying to do here. So the sooner we can get the ultimate off-taker and the ultimate off-taker backstops the project, then it moves fast, right? As fast as it can with lead times, right?
Mhm.
Thank you. These are really fascinating discussions, and thank you for the great insight. I'm going to send it back to Matthew, if that's okay. I think we're at the mark.
Thanks, Fengrong, and thanks to all for joining us today for this really timely, insightful panel. I really want to thank all of you for your insights, and hopefully we can revisit this topic down the road after more time has elapsed, and continue to keep our finger on the pulse of on-site and behind-the-meter energy for the data center industry, particularly in this AI era. So thanks to all.
Thank you very much.
Thank you, everyone.
Appreciate the opportunity.
Thank you.
Thank you.
You're very welcome. We'll see you next time on the Data Center Frontier Show podcast.